In stereochemical studies, one of the most fundamental concepts is that of chirality. And I think a good illustration of chirality could be seen by if you simply look at your hands, or feet for that matter. And what you will notice is that, this is a very poor drawing, is that your two hands look similar to each other, but they're not quite identical. And if you try to put one on top of the other, you will see that they will not match. And this relationship with an object is not superimposable with its mirror object. And your two hands are clearly mirror images of one another. It's called chiral. So these two are mirror images, but not superimposable. And hence they're chiral. Not all objects have the same property. For example, if you look at a table, again a very crude drawing of one, and its mirror image, these two things can be superimposed, and so they're achiral. While simple objects like a sphere, for example, share the same relationship, so they're achiral. And among other chiral objects, we can identify oftentimes objects that have something to do with our hands or feet, like gloves or scissors, for example. Probably notice it's very difficult to cut something with your left hand, or shoes, or screws, spiral staircases, for example. All of these objects share this common property that their mirror image and the object itself are not superimposed. Now, we wouldn't be talking about this if the same thing didn't apply to organic chemistry. So there are some organic molecules which can be superimposed with their mirror images, and some that cannot. And if you look at the simplest organic molecule, that is methane, and then we construct its mirror image, we'll realize that these two are identical. And if you don't see why and how are they identical, you might want to try to convince yourself by building a model and then rotating it around this axis by 180 degrees, which will get us to the exact same conformation of methane. And so this molecule is achiral. However, if we have a slightly more complex molecule, such as this one, in which we have several different halogen atoms in the same molecule, then we can also look at its mirror image. And what we'll see after rotation around the same axis, what comes out of this is that hydrogen is now turned to the left, as it was on the right before. Bromine was in the back left, now it's going to be in the front right, and fluorine in the back right. What we see now is that these two are not identical. Fluorine and bromine switch their positions, and so this molecule is chiral. And so this can be generalized now, that if we have a molecule that can be superimposed with its mirror image, it is achiral. However, if we have a molecule that cannot be superimposed with its mirror image, then two mirror images are two different molecules. So, non-superimposable images are different isomers of the same structure, of the same molecule. Isomers. Okay. So again, these two molecules, they have the same composition, same number of carbons, fluorines, hydrogens, and everything. They just have different structures, and so they're called isomers. And they're stereoisomers because their bonding sequence is not different. It's only their stereochemistry is different. And this specific type of stereoisomers is called enantiomers. And these enantiomers are the molecules that that have the same composition, but and look almost exactly the same, but are mirror images of one another and cannot be superimposed. Now this concept is challenging, and seeing these relationships in space, in three-dimensional spaces, it's very, very difficult. And so you should adamant that you should practice this with models and turn them until you're able to clearly recognize three-dimensional relationships, and furthermore to project those three-dimensional relationships onto the two-dimensional plane of the paper. Now, the question is, well, so we have these enantiomers, but is there a way to tell whether a certain molecule will have enantiomers or not? And the answer is yes. And so we simply, if we have a carbon atom and an sp3 hybridized carbon atom, and if that carbon atom has 4 different substituents, attached to it, it will be chiral. To illustrate that on an example, let's look at the substituted butane. There's a bromine here and hydrogen here. If we look at the mirror image of this compound, this is how it looks like. And now if we try to do our exercise, we'll turn it around this axis by about 180 degrees. What we'll get is something that is not superimposable to our starting material, because bromine is in the front and hydrogen is in the back. Unlike here where things are different. And so this is chiral. Okay? But what happens now if we switch one of the bromines, or switch the bromine for a methyl group? So now that we have two substituents of the same kind on this central carbon, two methyl groups. Now we can project this around a mirror image, and we get our mirror image. And we do the same exercise now, and we get something that looks like this. This thing is not quite identical to the thing we started with. But now if we do another rotation, and this will be now around an axis which is a little difficult to see, this one which goes through central carbon, the first carbon of the ethyl group. So we turn it around here from 120 degrees. We basically spin these 3 groups around this axis, and what we'll get is that they will switch their places. So this methyl group on the top will move to the background and replace hydrogen. The hydrogen will move to the front, and this methyl group that was in the front will move to the top. And now we get something which is identical with the thing we started. And so in other words, if we have a carbon which has 2 or more substituents of the same kind, some sequence of rotations, it may not have to be only one rotation, it can be multiples, will eventually get us to the identical structure. That will not be the case if we have carbon with 4 different substituents. In such carbons, the carbon with 4 different substituents can be called stereocenter, or asymmetric carbon, or chiral carbon, or chiral center, and is often denoted by a simple star to indicate its presence in a complex structure. Now this relationship is quite general, so if we have a nitrogen which has 4 different substituents, it will be chiral as well. Nitrogen that has 4 different substituents, however, is positively charged, but that's okay. So this will be a chiral ammonium salt, which has a chiral nitrogen in the middle. But now relationships, these relationships get a little bit more complex in compounds which have multiple chiral centers. And so to devise some general rules, if we have 0 chiral carbons, the compound in most cases will be achiral. A compound which has 1 chiral carbon is always chiral. But now a compound which has 2 or more chiral carbons can go either way, because these 2 chiral carbons can be oriented in a way that they enhance each other's chirality, or they can be oriented in a way which cancels their chirality, and in which case the overall compound is not chiral. And therefore that leads us to the sort of next subtopic, is the concepts of symmetry and chirality are intricately connected. Because if we have chirality in a proper symmetry, it will be cancelled out, and the overall compound will be achiral. And so a general rule here is that if a compound has an internal symmetry plane, and I'll show what it is in a minute, it must be achiral. Let's see what this looks like. If we look at 2 isomers of 1,2-dibromo cyclopentane, both of these carbons, if we look at them, are attached to 4 different things. This one is attached to bromine, hydrogen, CH2 group, and another CHBr group. Okay, so these are 4 different things, and the same applies to this one. And so this compound has 2 isomers. There is the cis isomer that I've just drawn, and the trans isomer, which is shown here. And both of them have 2 chiral centers. However, this compound has an overall plane of symmetry, which means that the 2 chiral centers are oriented in a way which cancels each other's chirality. And so this compound is overall achiral. Since here there is no plane of symmetry, this compound remains chiral. Plane of symmetry is often denoted by the Greek letter sigma, which should not be confused with the sigma bond. And so this is a sigma plane. Okay. Now, if you try to practice this, on some other molecules, we can look at relatively complex molecules such as this thing. And what we can recognize here is a plane of symmetry which intersects this in half. It goes through the plane of the screen, and so there is a plane of symmetry, and this molecule is achiral. The same conclusion applies to this molecule, even though it has 2 apparent chiral centers, because we've drawn this with these stereochemical denoters. It's easy to recognize that there is a symmetry plane here, and so that the molecule is achiral. But as soon as we see a molecule such as this one, where we have central carbon with 4 different substituents, then we can easily say that there is no plane of symmetry here. This is the chiral carbon, and this molecule is chiral. These symmetry considerations are very general, and they allow us to go back onto, for example, a carbon which has 2 substituents which are the same, and look at it again. And if we turn this just a little bit so that we get these chlorine and bromine atoms both into the central plane, which is perpendicular to the plane of our screen, that there is this central plane which encompasses carbon, chlorine, carbon, and bromine, then this central plane will intersect the molecule in 2 identical halves, and we will see that this is achiral, And we can reach this conclusion by looking at either of the two arguments, either at the fact that the carbon has 4 substituents but 2 are the same, or at the fact that this molecule overall has a plane of symmetry which makes it thicker. So the important thing is that you look at carbons in 3-dimensional space, you recognize the substituents on them, and you recognize symmetry elements. And that this common picture should create, should get to the common conclusion that molecule is chirally. So regardless of which criterion you use to establish the chirality, they have to be consistent. So all criteria, in other words, must get you to the same conclusion. Now, in the next section, we will see how we name these systems in an ambiguous fashion.